Welcome to qnawire.
We have two similar plates here, with the plate on the left being labeled as plate number 1, and this plate on the right is labeled plate number 2. And we know that the total mass of this system is 1.6 kilograms, so the mass of each plate is going to be equal to half of 1.6, which is 0.8 kilograms. And to start solving this problem, we're going to first find what the moment of inertia is in the x direction of plate 1 and also plate 2. So moment of inertia of the plate 1 is going to be equal to 1 over 3 times the mass m times the length b squared. So we can plug in m and we can plug in b. So plug in m and then we plug in b. And we'll get 3.84 times 10 to the negative 3 kilogram meters squared. And now for the second plate, plate number 2, this is going to be the same formula. So we plug in m and plug in b, and we'll get 3.84 times 10 to the negative 3 kilogram meters squared. So now the total moment of inertia about the x-axis this is going to be I of x1 plus I of x2. So I of x is equal to 3.84 times 10 to the negative 3 plus 3.84 times 10 to the negative 3, which then becomes 7.68 times 10 to the negative 3 kilogram meters squared. So now we're going to find the moment of inertia in the y direction of plate number 1 and also plate number 2. So for the first plate, I of y1, this is going to be equal to 1 over 3 times m times negative a squared. So we can rewrite this as 1 over 3 times m times a squared. So now I of y1 is equal to 1 over 3, and we plug in m, and we plug in a. And we'll get a value of 6.83 times 10 to the negative 3 kilogram meters squared. And now for the second plate, so the second plate, this sheet here, we see that it lies within the xz plane. So from that, we can say that I of y2 is just going to be equal to 0. So now I of y is equal to I of y1 plus I of y2. And since I of y2 is 0, I of y is just equal to I of y1. So I of y is just equal to I of y1. And now for the z direction. So I of z1 is going to be equal to 0, since if we look at the diagram, we see that this plate only lies within the xy plane. So there's no z component for the moment of inertia. And now for the second plate, I of z2, this is equal to 1 over 3 times m times a squared. So I of z2 is equal to 1 over 3, and we plug in m, and then we plug in a. So this becomes 6.83 times 10 to the negative 3 kilogram meters squared. So I of z is equal to I of z1 plus I of z2. And since we know I of z1 is equal to 0, I of z is just equal to I of z2. So next we're going to find what the moment of inertia is in the xy plane of the first plate. So I of xy of the first plate, this is equal to m times negative a over 2 times b over 2, which then becomes negative m times a times b divided by 4. So I of xy1, we start plugging in values. Plug in m, then we plug in a, and then we plug in b. And then this becomes negative 3.84 times 10 to the negative 3 kilogram meters squared. And for the yz plane, so I of yz, I of yz1 is equal to 0, and also I of zx is equal to 0. Since the first sheet does not lie within the yz plane or the xz plane, it only lies within this xy plane. So now we're going to work with the second sheet. So for the second plate, we write that I of xy2 is equal to 0, since it does not lie within that xy plane. And we're going to write that I of xz2 is equal to m times a over 2 times b over 2, which becomes m times a times b divided by 4. So now I of xz2 is equal to m times a times b, and this will give us a value of 3.84 times 10 to the negative 3 kilogram meters squared. And now the total moment of inertia in the xy plane is equal to I of xy1 plus I of xy2. So now I of xy is equal to just negative 3.84 times 10 to the negative 3. Now we do the same thing for the y direction, for the yz plane. So I of yz is equal to I of yz in the first plate plus I of yz in the second plate. So we know so this is 0 for both planes. So I of yz just becomes 0. And now I of xz is equal to I of xz1 plus I of xz2. So then this becomes 3.84 times 10 to the negative 3 kilograms meters squared. So now to solve for our angular momentum, we need to find the x, y, and z component of our angular momentum. So we're going to go back to the top here and clear out some calculations to make more room. So I'll clear this out, and then I'll clear this out. Okay, so for our x component of the angular momentum, h of gx, this is equal to I of x times omega x minus I of xy omega y minus I of xz omega z. So then we can plug in so we plug in I of x, and then we plug in omega x, then we plug in I of xy, then we plug in omega y, then we plug in I of xz. Then omega z. So this becomes 0.1536 kilograms per kilogram meters squared per second. Now for the y component, h of gy, this is equal to negative I of xy omega x plus I of y omega y minus I of yz times omega z. So we can plug in values, and the only important values are I of xy and omega x, since the angular velocity in the y and z direction is just going to be equal to 0. So this then becomes 0.0768 kilograms meters squared per second. And now we do the z direction. So h of gz is equal to negative I of xz times omega x minus I of yz times omega y plus I of z times omega z. So we start plugging in values. So we plug in I of xz. So this becomes 3.84 times 10 to the negative 3, and then times omega x. And then we know that the angular velocity in the y and z direction is equal to 0, so we can ignore the other terms. So now this becomes negative 0.0768 kilogram meters squared per second. So we now have all our necessary components, all our necessary vector components to write our final angular velocity, or angular momentum. So this angular momentum, we can now write it as 0.1536I plus 0.0768J minus 0.0768K kilogram meters squared per second.